Internal energy and the first law recap. Energy in phase changes. Before we introduce internal energy, let's quickly recap something we already know. When a substance melts or boils, energy is absorbed, but the temperature does not change. That energy is used to break intermolecular bonds, not to make particles move faster. This energy is called latent heat. A simple example is ice melting in a drink. The ice absorbs energy from the drink, which cools the drink down, even though the ice itself stays at 0 degrees Celsius while melting. Latent heat and internal energy. Thinking deeper. Let's think more carefully about what's happening to energy. Have a go at these questions in your book. Write what you believe is the correct answer and explain it. Pause the video and then we will go through the ideas together. Latent heat is energy absorbed or released during a change of state without a temperature change. Temperature stays constant because the energy goes into breaking bonds, not increasing particle speed. Even though temperature stays the same, something is changing: the internal energy of the substance. During melting, the internal energy of water increases because the potential energy of the particles increases, even though their kinetic energy stays the same. What is internal energy? So what exactly is internal energy? Internal energy, usually called U, is the total energy of all the particles in a system. It has two parts. The kinetic energy component comes from particle motion. This is directly related to temperature. Higher temperature means higher average kinetic energy. The potential energy component comes from the bonds between particles. This changes during phase changes, compression, or expansion. Internal energy is the sum of both kinetic and potential energy. Internal energy analogy: a bank account. A useful way to think about internal energy is like a bank account. The balance in the account represents the internal energy of a system. Heat and work are like deposits or withdrawals. They change the balance, but they don't create or destroy money. In the same way, energy is conserved. It is only transferred between systems. The first law of thermodynamics. This idea leads us to the first law of thermodynamics. The first law states that the change in internal energy of a system is equal to the heat added to the system plus the work done on the system. We write this as delta U equals Q plus W. Understanding the sign convention is very important. Heat, Q, is positive when heat is added to the system and negative when heat leaves the system. Work, W, is positive when work is done on the system and negative when work is done by the system. For example, when you pump air into a bike tire, you do work on the air. That means W is positive and the internal energy of the air increases. Analyzing energy changes. Step by step. Whenever you apply the first law, follow this process. First, clearly define the system, for example, gas inside a cylinder. Next, ask whether heat is added or removed. Look for things like flames, heaters, cooling, or insulation. Then, check whether work is being done. Is the system expanding or being compressed? Finally, use the equation delta U equals Q plus W to find the change in internal energy. Compressing a gas. Let's look at an example. If a gas is compressed, work is done on the gas, so W is positive. If there is no heat exchange, Q is 0. That means delta U is positive. The internal energy increases. As internal energy increases, particle kinetic energy increases, so temperature rises. This is why a bike pump feels warm when you inflate a tire, heating a sealed container. Now consider heating a sealed, rigid container. Heat is added to the system, so Q is positive. The container cannot change volume, so no work is done. W is 0. All the added energy goes into increasing internal energy. particles move faster and the temperature rises. Everyday applications. These ideas appear everywhere in real life. In a car engine, fuel burns and heats gases. The gases expand, doing work on pistons and converting energy into motion. In a refrigerator, the compressor does work on the coolant, increasing its internal energy before heat is released outside. In the human body, metabolism adds energy, which we use to do work and release heat to maintain body temperature. In a hot air balloon, heating air increases internal energy. The air expands and work is done lifting the balloon. Internal energy and the first law quiz. Let's check our understanding. Pause the video here and have a go at answering the following questions. When you're done, press play and we will go through them together. When ice melts, its internal energy increases because energy is used to break bonds, increasing potential energy. Temperature stays constant during melting because kinetic energy does not increase. The first law of thermodynamics states that the change in internal energy equals the heat added plus the work done on the system, written as delta U equals Q plus W. Why this matters. Understanding internal energy and the first law is incredibly important. It helps engineers design more efficient engines and heating systems. It supports climate technology by improving energy conversion and reducing waste heat. It guides the design of medical devices that require precise thermal control. And it underpins future energy systems from solar thermal power to nuclear energy. Final summary. Let's finish with the key ideas. Internal energy is the total kinetic and potential energy of particles in a system. The first law of thermodynamics shows that energy is conserved. Heat and work are energy transfers that change internal energy. These principles explain real systems ranging from engines to refrigerators to the human body.